Okay, so let's start. First of all, these glasses, I will be wearing them only this hour, hopefully. And what they do is they will track where I am looking at in the class. So one of the good practices in teaching is to have some eye contact with the students. But that becomes somewhat problematic in large classrooms like this one. Especially, I have a tendency to look in this directions. But I rarely look in that direction, and well, in that direction I kind of look because I'm somewhat positioned towards this side. But I rarely look at that side. So that's why your friends who are planning to play with their cellular phones, they usually tend to sit on that region. And well, hopefully I will be sharing with you the results probably next week. I will have the heat map by next week. So okay, back to our subject. So do you have any questions? If you remember, the last thing we were discussing was how to calculate the electric field for various continuous charge distributions. Like we had looked at the infinite wire, and we found that at a distance, let's say d from the wire, the electric field, assuming the charge has a linear charge density lambda, if it is positive, it will be pointing away from the wire. If it is negative, it will be pointing towards the wire. And the magnitude was given by 1 over epsilon 0, lambda over 2 pi d. And then we had the infinite plane. This is wire. This is infinite plane. And we had seen that the electric field magnitude was just sigma over epsilon 0, independent of the distance. And again, if sigma is positive, it is pointing away from the plane. And if it is negative, it is pointing towards the plane. And especially in the case of this infinite sheet, what we had imagined was we started with a ring charge distribution. And along this line passing through its center, we picked up a point. Let's say the ring had the charge q, and this was at a distance, let's call it again d. And the ring, if the ring had the radius r, the electric field was pointing again away from the ring if the charge is positive, and towards the ring if the charge is negative. And the electric field was given by 1 over 4 pi epsilon 0. Q times d over d squared plus r squared to the power 3/2. This was the magnitude of the electric field. And then we said, okay, if we have a point over here on top of the infinite plane, if you consider the direct projection on the plane, if it is right over here, the projection at a distance, again, let's call d, we just imagine the infinite plane made up of very thin, infinitely many rings centered around that point with increasing radius, and then just summing over the electric field that we calculated over here for the ring, summing over the electric field created by each one of these rings, we could calculate the electric field created by this infinite plane, and this is what we obtained. So the idea is essentially, if you have any continuous charge distribution, first, you divide it into smaller charge distributions whose electric fields you know. It doesn't have to be point charge. To calculate this infinite wire, we divide it into very small segments, which we treated as if they are a point charge. And then, using the expression for the point charge, we could just sum up to obtain the wire. In the case of the plane, we already knew what the electric field of a ring is. So we used that result. We divided the plane into infinite rings, infinitely many rings, and calculate the electric field. Or, in fact, we could have also done something else, which will be a bit more complicated. That's why we didn't do it. We can imagine this plane as a set of infinitely many lines. So we already know that result. We would use that result to calculate the electric field of one of the wires. Let's say we should get the identical result. I could have imagined that plane to be made up of infinitely many, well, these are straight, infinitely many such thin strips. They can all be treated as a wire, and if I just sum all the wire up, I should get exactly the same result. It's left as an exercise. Now, any questions up to here? Now, most of these cases, the physics basically ends when you write the integral. Can you identify the, for example, the plane as a collection of wires or a collection of rings? And once you make that identification, you can just write the electric field of each one of the segments, sum them up, that is an integral, and the rest is basically calculus. Now, let's look at another example. This is the properties. We have been discussing the properties of electric field. Let's see how the electric field interacts with conductors or metals as a particular case. Well, most of the arguments that we will be using now will be valid for any conductor, but as a concrete example, I will be discussing metals. Now, I also would like to remind you that for the time being, we are looking at electrostatics. So what I mean by this is that nothing is moving. Well, we know that electric fields can exert forces on our system. So the various parts of the system might be moving. As long as they are moving, we are not in the electrostatic case. So our results might not be valid in that case. So that is something you should keep in mind. Now let's imagine such a conductor. And let's assume that it is in a region where there is an electric field outside, electric field everywhere. So at this point, there is such an electric field. At this point, there is such an electric field. Again, for simplicity, we can just assume the electric field to be uniform. Now, let's imagine at first, when we put this conductor inside our electric field, at that moment, there is an electric field also at this point. A non-zero electric field. So what distinguishes a conductor from a non-conductor?
It's more permeable to magnetic.
What else? We didn't study magnetic fields yet. You see, for the time being, we studied the electric field and the charges and the forces acting on charges. So what distinguishes a conductor from an insulator? Well, in the case of the metal, there are free electrons. In general, the conductors are objects which contain free charges, that free in the sense that they can move around. So you see, I have this metal. In the metal, it's the electrons that are moving. The nuclei will be fixed. So at this point, there is an electron. Initially, when I put this conductor, the electrons were in their original places. I put the conductor inside that electric field. There is an electric field at that point. There is an electron at that point. So what will be the direction of the force acting on the electron? Leftwards. So remember, the force acting on any charge due to an electric field will be just the electric field multiplied by the charge. Well, this is the electric field at the position of the charge. So here, if there is an electron, the force it will feel will be the electric field at that point multiplied by the charge of the electron. Well, the charge of the electron is negative. So here you have a vector which is pointing in that direction multiplied by a negative number. Well, a negative number just changes the direction of the vector, so the force will be in that direction. So the electron will feel a force in that direction. Well, the electron is free to move as long as it is inside the metal. So there is a force acting on it. So it will just move. It will move until it reaches this surface. Well, imagine that there are everywhere, at this point also there is an electric field. So the electron here will also feel a force in that direction. The electron here will also feel a force in that direction. But if the charges are moving, we are not yet in electrostatics. The system is changing with time. So the system is not yet static. But what will happen? As time goes on, these electrons will start accumulating over here. Well, on the other side of this metal, on this surface, the electrons had already moved towards the left. So there's a reduction in the number of electrons. There are excess positive charges there. So the other side will be positively charged. Well, here we have a positive planar charge distribution. Here we have a negative planar charge distribution. These charges will create an additional electric field. You see, there is this electric field which is created by the charges outside my metal. Now I have some charge distribution inside my metal. So here there is an additional positive charges. Here there is additional negative charges. These charges will create an additional electric field. In which direction will that additional electric field be? Well, the electric field is always pointing away from positive charges and towards the negative charges. So this electric field will be the electric field created by these charges will be in the opposite direction. This is the additional electric field. So here there will be in this direction, here it will be in this direction, here it will be in this direction. Now let's see. This additional electric field will keep on increasing as long as there is charge accumulation on these surfaces. So as long as the charges are moving towards, the electrons are moving towards the left, this additional electric field will increase and increase. But then there will come a point when the magnitude of this additional electric field will be equal to the magnitude of the external electric field. At that time, the total electric field will be 0. If the electric field is 0, then there won't be any force acting on the electrons. Do you follow? So essentially, the charges are accumulating at both surfaces of my conductor, and they are creating this additional electric field in the opposite direction. So in a sense, if you consider this electron over here, they feel a force due to this external electric field. But now there are positive charges over here which is pulling these electrons towards the right, and these negative charges which is pushing that electron again towards the right. And the magnitude of this additional force is increasing as long as the electrons are accumulating on this surface, and this surface just becomes positively charged. So that magnitude will keep on increasing until this additional electric field created by these induced charges will balance the electric field that we applied. But at that moment, the electrons will not move anymore because they are not feeling any net force. But if they are not feeling any net force, they are not moving, now we are in our static configuration. Now we can apply our concepts of electrostatics. But when the system reaches statics, so basically what will happen is, so this is our metal. Outside the metal, the electric field will be non-zero. Well, basically because we are applying an external electric field. Here we have two parallel plates, and in the two parallel plates, the electric field is non-zero only in the inside. They don't create any electric field outside, so they do not change the electric field outside, at least in this case. But inside, now we have an electric field which exactly balances the applied electric field. So inside the metal, we don't have any electric field. So this side of the metal is negatively charged. This surface is positively charged. Now, basically, we can apply the same principle to more complicated configurations also. Let's see. Suppose we don't place it, we don't have such a regular shape, but we can imagine an irregular shape. Well, the basic idea will still hold. If there is an external electric field, the charges inside will move around until the electric field created by these induced charges exactly cancels the external applied electric field. So when statics is reached, again, we won't have any electric field inside. Because otherwise, if there is any electric field left inside, that would mean that the electrons inside my conductor will be moving around. Well, that would mean I haven't yet reached the static configuration. Now, let's look at what happens on the surface, though. Let's imagine that this is our conductor. At this point, we already know that inside the conductor, the electric field should be 0. We didn't say anything about what happens to the electric field outside. Let's look at right at this point on the surface. Let's imagine that there is an electric field at that point, pointing, let's say, in this direction. At a given instant, let's say that the electric field is pointing in that direction. But still we have a problem. If that happens, we are not in statics. You see, what will happen? I can imagine a coordinate axis at that point, one perpendicular to the surface, the other one tangent to the surface. Now, this electric field will have a tangent component. Let me call it E parallel. It's parallel to the surface, and a vertical component. This is E parallel. This is the vertical component of the electric field. You see here, the electron cannot leave the metal. It is confined inside the metal. So this electric field will exert a force. Let me just change the direction of this electric field. It will be easier to show. Let's assume that this is the direction of the electric field at that point. Again, it has a horizontal component, horizontal to the surface, and a vertical component. To calculate the force exerted on an electron, just multiply these electric fields by the charge of the electron, which is negative. So this horizontal component of the electric field will exert a force in the opposite direction, but still parallel to the surface. And the vertical component will exert a force on the electron vertical to the surface. Now, the metal will not allow the electron to leave the metal. So there will be forces acting on the electron, not shown here, due to the metal. Those forces will prevent the electron from leaving the metal, but it will allow the electron to move freely inside the metal. So this force will not create any motion because of the forces created by the conductor, by the metal itself. But there is this horizontal force. The electron is free to move horizontally, because if it's moving horizontally, it's not leaving the conductor. So if there is such a component to the force, the electrons will be moving around. But that again means that we are not in the static case. So when the statics is reached, again, this parallel component will be exactly 0. Now, what this shows us is that the electric field on the surface of a conductor is perpendicular to the surface. Let me emphasize, this is in electrostatics. When we put the conductor inside an electric field, or when we change the electric field, the electrons will be moving around. So it's no longer statics. But if you wait long enough, eventually the electrons will reach their final position. And when they reach their final position, the electric field inside the conductor will be 0. And the electric field on the surface of the conductor will be perpendicular to the conductor itself. These are the two things that you should keep in mind. Any questions on these? Now we will come back to this problem of electric fields and conductors later on also. So let's just go forward with electric field lines. In a sense, we had already defined it, but we just passed it very quickly. So I just would like to review what we call the electric field lines, how we define them. Because the idea in defining the electric field lines is mainly to visualize how the electric field in various regions of space looks like. You see, in the examples that we had been discussing, for example, here, I tried to draw many electric field vectors at different points. But if you want to show more electric vectors, then it becomes both cumbersome and not practical. So what we do is, for example, if you look at a point charge, let's say, now the electric fields are always pointing away, that we know, that we had already discussed. So they will just look like this. They will get smaller as we are moving away from the charge. Ideally, you should put a vector at every point in space. But you already see a pattern. You see here all these vector fields are just pointing in the same direction. It's as if they are lying on this line. Here they are also lying on the same line. Here they are also lying on the same line. So we draw lines that at every given point the lines should be tangent to the electric field at that point. So in this case, this is an electric field line. Well, let me use a different color. This is an electric field line. This is another one. These are all electric field lines. Well, how many electric field lines are there? Well, it depends on your choice. You can pick up whichever you like. You can choose, for example, if you are working with charges that are thousands of coulombs, you can say that for each coulomb you will draw one electric field line. Or if you are working with just a few coulombs, you can say that for each coulomb you will draw, I don't know, 1,000 electric field lines to get an idea. It's just up to you. Just once you fix your convention, you have to stick with it. I mean, once you decide that for each point coulomb you will use 1,000 electric field lines, then for every coulomb you should use 1,000 electric field lines for all the charges in your problem. Now, what else you can see in the simple case? Well, you see they spread out. Since they are radially moving outward, they will be spreading out. So this is a point where the electric field is less intense. The magnitude of the electric field at this point is larger. This is a general property of the electric field lines. They are less dense in regions where the electric field has a smaller magnitude, and they are denser in regions where the electric field has a larger magnitude. So the properties of electric field lines can be summarized in two statements. One, electric field lines are electric fields at a point is always tangent to the electric field line passing through that point. Well, the tangent basically has two directions. So to specify the direction, we also put some vectors, some arrows on the lines. So in the simple case, I was imagining that I have a positive charge over here, so all the electric fields are pointing away from the positive charge. So I just imagine this line as if it starts from the positive charge and moves away. Another important property of the electric field lines is that the electric field magnitude, you see, if you want to specify the electric field at a given point, you have to specify two things. Since it's a vector, we have to know its direction, and we have to know its magnitude. So the tangent to these field lines already gives me the direction. I have to also have some means of specifying its magnitude. And the magnitude is just like we have seen in this simple example. The magnitude of the electric field at a given point is proportional to the density of the electric field lines at that point. Well, you see, here the density is defined for continuous things. For example, if you have a continuous mass distribution, you define the mass density. If you have a continuous charge distribution, you have a charge density. In sketches, if you want to draw the lines, you draw a finite number of lines. So they will not be continuous. But just imagine them for every practical problem. If you would like to use the electric field lines to determine the magnitude of the electric field, you have to draw many electric field lines so that they can be almost treated as continuous. Now, this property is valid because the electric field, the Coulomb law, has this 1 over r squared behavior. Now, how is that relevant? Well, you see, here we have a positive charge. And we draw this, if you like, let's say 20 electric field lines. Now, if you just imagine spheres around that. Let's say there is such a sphere. How do you calculate the density? Well, you just count the number of electric field lines divided by the surface area. Well, the surface area is 4 pi r squared. So the density over here is proportional to 4 pi, inversely proportional to this 4 pi r squared, which is just the Coulomb's law. And if you just would plot, I don't know, another sphere around it, since the number of field lines does not change in this region, the density, well, assuming it's in this problem it's uniformly distributed on this sphere, so to calculate the density at a given point, just divide the total number, which is already fixed by the charges over here, and divide by the total surface area, which is again 1 over r squared, 1 over the 4 pi r squared, this time the radius of the larger sphere. So at any given point, well, this just tells me that if this is true, if the intensity of the electric field, the magnitude of the electric field is proportional to the density, it already tells me that the electric field should be a 1 over r squared law. If it is 1 over r cubed, this will not hold. Now, let's do an example. We already looked at the dipole. Electric field lines of a dipole. So here we have a plus q charge. Here we have a minus q charge. Well, we had already calculated that if you imagine this, well, let's first plot this line and then draw the perpendicular line to it passing through the center. We had already calculated the electric field at that point. It was horizontal. Well, what we had done was this positive charge will create an electric field in that direction. This negative charge will create an electric field in this direction. When we sum them up, we will have a horizontal electric field. So we know that here the electric field is horizontal. Now, if we are very close to, let's say, the plus q charge, somewhere over here, well, remember, the electric field will be the constant 1 over 4 pi epsilon 0 multiplied by q divided by the distance squared. Well, if the distance is very small, then the electric field magnitude is huge. So at this point, the electric field created by this plus q charge will be huge, whereas the electric field created by this minus q charge will be much smaller. So the electric field, if we ignore that, the electric field over here will be just pointing away from the positive charge. So at that point, the electric fields will point in this direction. Well, we can do the similar argument very close to this minus q charge. Again, very close to the minus q charge, the electric field created by this charge will be huge, whereas the electric field created by the plus q charge will be much smaller, so we can just ignore it. So the electric field at this point will be just pointing towards the charge. And huge. Well, these limiting cases already tell me how my electric field lines should look like. You see, the electric field line at any point should be tangent to that vector. So if we start from here, well, the electric field line should be tangent to these vectors, so it will start moving in that direction. When it reaches the negative charge, it should be going straight into the radially into the minus q charge, negative charge. And in between, it should become horizontal along that line. So if I would just connect the dots or connect the vectors, my electric field lines will look like this. Well, if I start from here, it will first go out, but it should bend towards the minus q charge. So this is how the electric field lines will look like. Only the electric field line that is along this line will go up to infinity, will come from infinity. And this one, along this horizontal line, will go up to infinity. All the other ones, if I would draw an electric field line moving in that direction, it will eventually bend and come here. If I would draw one starting in that direction, it will eventually bend and come to the negative charge. Well, let's imagine a different case, a case we didn't solve. Let's imagine there is a plus 2q charge over here and a minus q charge over there. How the electric field lines will look like in this case. Well, again, we can just mainly use the same arguments. Very close to this charge, the electric field lines should be radially out. Very close to this one, the electric lines should be radially in. So here they will start in this. Let me just draw some directions. And for this sketch, I will be drawing, let's say, 8 charges, 8 lines for a charge 2q. So here I should only have 4 of them. Because there is just a charge q, I should only draw 4 of the charges. In this horizontal direction, not the horizontal, in this vertical bisector, along that line, now the plus 2q charge will create a larger electric field at a given point than this one. So it won't be horizontal. At this point, it will be pointing somewhat away. It will be inclined away from the horizontal line. So let's see. If I start from this one, it will move like this. It is pointing away, but then it will bend down. This one will just go straight. This one will first move away and then towards my charge. This one will start out, but then it will bend along that dashed line. It will be somewhat still pointing upward and then bend down. And this one, it will also look something like this, etc. This will go to infinities. So this is how the electric field lines will look like. And here the density is large, so the electric field here is large. The electric field here is large. The electric field in this region is somewhat the smallest, because the density in that region in that region, the density of the field lines is smaller, so the magnitude of the electric field in these regions. In this one, it was this vertical line, but in this one, in this region, it will be smaller. So kind of these electric field lines allow us to visualize how the electric field looks in various regions of space. Now let's combine this with our discussion of the conductors. So before we were looking at conductors, we said that inside the conductor there won't be an electric field. Well, that basically tells us that whatever electric field line we draw, those lines should not go into the conductor. So if you have, let's say, very far away, you have a uniform electric field. Well, uniform electric field means its direction is the same. So the electric field lines, they are parallel. Uniform means the magnitude of the electric field doesn't change. So the density of the electric field lines should also be the same. So they should be equally spaced. Now, if you put a conductor, well, they will reach the conductor and stop there. Here we have negative charges. The electric field lines ends on negative charges. Well, on the other side, we have positive charges. And new electric field lines will start from the positive charges and go to infinity. Well, if we imagine let's say, a spherical conductor, and if the electric field far away is uniform, well, we are just have a uniform electric field and then place a spherical conductor inside. Well, the conductor will not affect the electric field at far away distances because it is neutral. But what will happen is, as the electric field line approaches the conductor, you see, we had said that the electric field on the surface of a conductor should be perpendicular to the surface, which means since the electric field is tangent to the electric field line, this line should be perpendicular to the surface. So without the conductor, even if the electric field line is horizontal, with the conductor, it should bend so that it will be perpendicular to the surface. This, again, will bend slightly. This will bend slightly. This will bend strongly. So that the electric field lines at every point on the surface will be perpendicular to it. And again, here, as it's approaching, it should bend. This is already almost perpendicular. So these are the electric field lines. So whatever the shape, just paying attention to the fact that, one, there is no electric field line passing through the conductor, and two, the electric field line should be always perpendicular to the surface of the conductor. You can sketch the electric field lines and try to guess where the lines are stronger, where the lines are denser, you will have a larger electric field. Where the lines are more sparse, you will have a weaker electric field. So without solving any calculus, any integrals, etc., you can have an idea in which regions the electric field will be strong, in which regions it will be weak.
Hocam peki çıktıktan sonra neden yatay ilerliyor da düz bir şekilde devam etmiyor?
You see, the idea is this one. I already have a region of space where there is a uniform electric field. It is horizontal. Then in this region, I put a conductor over there. Well, since it will be able to modify only what happens near it, it will have no effect in this region. So eventually it should become horizontal. So again, if you look at our earlier discussions, what is happening is we already have this horizontal electric field everywhere, which is inducing some charges on this sphere. So it will be, here we have some negative charges, since the electric field lines are ending at those points. Here we have some positive charges, since the electric field lines are starting over there. But this time, the electric charges, we cannot think of them as infinite planes. They are just localized in finite regions. So this will be creating additional electric fields in this direction, which will cancel the external electric field inside, but it also creates an electric field, let's say, in this direction. And in this direction, these will be additional electric fields modifying the total electric field in the near vicinity, not in the faraway distances. So the total electric field will be the applied electric field plus the electric field created by these induced charges. But these induced charges will create an electric field only in the near vicinity, because basically this is a neutral object. From a far away, you will not see any charge. Any questions? Well, let me just write one more thing. We will pick up on Thursday. Here I have been using another law, the Gauss's law. Which, at least in the terminology that we have used, basically states that the number of electric field lines is constant in regions of no electric charge. So what I have used throughout is that the electric field lines should should end in negative charges, and they should start on positive charges. I cannot just have an electric field line starting from this empty vacuum. It just doesn't happen. That is the statement of the Gauss's law. So we will be doing more mathematical description of this, but the essence of the Gauss's law is just the number of electric field lines is conserved, in the sense that it starts from positive charges, ends in negative charges. It cannot start or terminate in regions where there is no charge. It cannot split into two. Okay, see you on Thursday.